Great. Thanks, everyone. Thanks for getting down here early. Thanks for putting us on the program. This is joint work with Semyon and Malamud, who I have a pretty large machine learning agenda working on, and one of my outstanding students at Yale, Kangying Zhou. And let me thank Andreas in advance for discussing a paper. It's actually already forthcoming, so I know that's not the most pleasant position to be in as a discussant. We'll still look forward to your input for kind of the broader agenda. Okay, so this is about, we're calling it the virtue of complexity. When we talk about complexity, what we're talking about are highly parameterized models. All right, this is a phrase that gets used in the machine learning literature. In particular, it's talking about the ratio of the number of parameters in a model to the number of observations that you have in a training data set. Okay? All right, now, I think a good place to start is to think about the principle of parsimony. All right, so this is how I, as an econometrician, was originally raised, from this perspective of a principle of parsimony. And if you come from this kind of time series lineage that I was trained in, you know, a core resource is this Box and Jenkins textbook. This Box and Jenkins textbook starts off with about 4 different rules of how to build models effectively. And this is literally rule number 1 in chapter 1 of their textbook. It is important in practice that we employ the smallest possible number of parameters for adequate representations. All right. Now, I want to contrast that with modern machine learning. Okay, so everybody in this room has seen ChatGPT, right? We have massive parameterizations that are at work in the real world via machine learning. Okay, so take, for example, the model that underlies ChatGPT. It's called GPT-3. Right? This model has 175 billion parameters in it. And there's now a ChatGPT-4 that's developed, it's not released yet, has 1 trillion parameters in it. I've been working on models that are big models for asset pricing. Even my big models, they're puny by this standards, we're talking about 30,000 parameters in an asset pricing model. Right? You would think that then, to a Box Jenkins econometrician, this seems sort of silly, profligate, right? Probably prone to overfit and likely to be disastrous out of sample. Turns out this is totally wrong. It turns out that the bigger you make a model, the better its tendency to perform out of sample. And that's what this paper is about. All right? So this is a fact that's become a very hot topic for understanding in the machine learning community. So for example, there's this beautiful paper by Misha Belkin at Berkeley. He's a machine learner. He points out that in a lot of the standard machine learning problems, the best performing model out of all of the models that have been studied for things like image recognition or text prediction, they're always the very largest model that's been trained to date. All right. So it seems that modern machine learning may be turning this principle of parsimony on its head. All right. Now, what I want to talk to you about is that this is happening in finance too. All right. So in the finance literature, we've had some what I'd characterize as very fast advances and improvements in asset pricing models using machine learning methods, using highly parameterized methods. Right? We've documented a lot of large empirical gains over simple models. I've done this in my work. My discussant has done this in his work. There's a large literature that's starting to develop around this. The issue is that there's not a whole lot of theoretical understanding for why this is happening. Right? And I would also say that because of this lack of theoretical understanding, there's a lot of skepticism out there as well. So if I want to kind of cast this paper, the main point of why I wanted to write this paper is because I want to build the case for doing financial machine learning. The main theoretical result that I'm going to show you, when I say theoretical, now we're talking about statistical theoretical result, is that portfolio performance derived from machine learning models, right? So I estimate a machine learning model, I use that to build an optimal portfolio. That performance is generally increasing in model complexity. The more parameters you cram into that statistical model, the better the out-of-sample performance you should expect from that model. Right? So what I want to do in this talk is explain the intuition for why this happens. It turns out that the intuition is not that difficult to get your arms around. We're going to try and do it kind of thinking through basic logic of least squares. Right? And then I'll have a small empirical result at the end that provides some direct empirical results for for this statistical theory. Okay, so to formulate the problem, let me kind of cast it as a bit of a thought experiment. So suppose you have an analyst who's doing some research. Right? They want to build a forecasting model. They want to forecast, say, market returns using some information, some variables. I'm going to call those variables G. All right? These can be standard predictor variables. In my thought experiment, I'm going to think about the analyst as knowing what the relevant predictor variables are. What the analyst doesn't know is the true prediction function, f. All right? So what should an analyst do when faced with this kind of problem? Well, a standard machine learning approach would be to say, I'm going to use that predictive information. Because I don't know the functional form, I'm going to use a generic approximating model, a non-parametric model. For example, a neural network. All right? And the way a neural network works, it's just a basis expansion. Right? It's just like doing a Taylor approximation to f, but instead of doing polynomials, we're going to use different bases. Okay? So what the neural network really does is it takes these G's and it transforms them into what we can call engineered features or engineered predictors. All right? The important thing is that we're going to build many potential engineered features. Right? We're going to start with G. G may be a big number, maybe a small number. In our application, it's going to be like 15 predictor variables. But then from those 15 predictor variables, I'm going to produce many, many nonlinear functions of those predictor variables, trying to cover all the ways that the information in that G could be relevant for prediction. The logic behind this is exactly a neural network. All right? So I start with my original data, the G variables. I expand it out into all of these basis functions. Right? I expand the way that I could access the information contained in the G. Then at the end, what I'm left with boils down to a linear regression. But instead of regressing the return directly on the G, I regress it on this expanded set of basis for G. All right. So that's the way that in this thought experiment, I'm going to imagine an analyst pursuing this prediction problem. All right, so I have my true model that I can't access because I don't know f. I have my generic approximating model. And right away, I can think about, OK, here's the tough question that the analyst has to answer. How big should I make that approximating model? How many nodes should I put in that neural network? How many basis functions should I have to approximate f? That's the question. All right. So we're going to think about this as the analyst has a fixed amount of data. You just have t observations to train on. You have to pick p. Which p should you choose? All right. The trade-off is pretty straightforward. If I use a simple model, p much smaller than t, think about our more traditional models. This has some nice aspects. For example, it's going to be a low variance model. Because I have significantly more observations than parameters, I'm going to be able to inform those parameters fairly well. They're going to have low variance when I bring them out of sample. But it's costly to do this. If I only use a small amount of p, I'm going to end up with a coarse approximator of f. I'm going to have model misspecification. I could go the other way, though. I could use lots and lots of parameters. I can make my approximation extremely rich, make p very, very large. This will give me a good approximator. It'll essentially allow me to eliminate model misspecification to whatever degree I seek. The cost, of course, is then I have to estimate all of those parameters. And that might make my model behave poorly when I bring it out of sample. So that's the question. Which p should I opt for? Does adding more parameters, getting a better approximation, justify the cost, the statistical cost? Think of it as the variance cost of adding those parameters. It seems like it's not going to be very clear-cut which way we should go on this. But the answer is totally unambiguous. You should use the largest p that you can compute. If you can compute an infinite approximation function, use an infinite number of parameters. Okay, so the rest of the talk is going to be trying to draw out why this actually happens. All right, so the environment that I'm working in, it's going to be extremely straightforward. I'm going to be thinking about a linear prediction model with a single asset that I'm trying to forecast. So think about this paper as being about the market timing problem. I'm going to allow a large set of predictor variables S. Okay, it's going to be p predictors, and of course, a lot of what we're going to be talking about here is what happens as we vary p. Right? This linearity is without loss of generality because do a lot in paper thinking about these S's as these generated regressors. You might start with a small feature set originally, but you expand it out to a big feature set. And once you do that, you're basically back in the realm of linear models. All right, I'm going to put some assumptions on the beta here. Okay. One important assumption is that the total predictability in this model is going to be fixed. As I change P, I'm going to not want to change the amount of true predictability in the model. Why is that? Because if I allowed predictability to scale with P, I'd get infinite Sharpe ratios eventually. All right. Now, when I take this prediction model, I'm going to be estimating this prediction model. I need to ask, how do I then convert that into something finance related? Right? How do I build a trading strategy? And the trading strategy we're going to work with is a very simple one. It's going to be a simple linear market timing strategy. So once I get my return forecast, I'm just going to use that return forecast to scale my position up or down in the market. All right. Okay, so that's the environment that we're working in. It's a simple one. What do I want to get out of this? So the goals of the theoretical analysis is to characterize expected out-of-sample behaviors. One thing that we have to be extremely cognizant of, that we have to get very used to as we move to thinking about machine learning and finance, is that in-sample is no longer relevant. Why? Because when I use big models, I can fit in-sample arbitrarily well. It's all about thinking what can happen when I bring these big models out of sample. So I want to characterize expected out-of-sample behaviors, things like prediction accuracy and portfolio performance. Nothing I'm going to show you is going to have anything to say about in-sample. In-sample is uninteresting when you do machine learning. It's all about the out-of-sample. Second, I want to emphasize very high P results, okay? So I'm going to be thinking about what happens when I push complexity to kind of astronomical levels. All right. The tools to do this require us stepping out of traditional asymptotic theory. When we do traditional asymptotic theory, you can effectively think of it as fixing P and then taking T to infinity. That's what is, in our setting, a zero complexity model. If the number of observations go to infinity and P is fixed, I have no model complexity. I have all the data I need to inform my estimates. That's not how machine learning works, though. We have finite training sets, but we can make arbitrarily big models. So we kind of need to go the other way. We have to ask, what are the asymptotics when P goes to infinity? All right, so I'm in particular going to be thinking about this model complexity object, C, as being core to describing the behavior of machine learning models when I bring them out of sample. All right. Now, to derive these results, fortunately, we have some great theory that's been developing over the past couple decades. That's exactly the theory you need to characterize these types of limits when the number of parameters become very large. Okay, it's random matrix theory. Okay, now, next step. That's the framework. That's what I want to accomplish. I'm going to try to provide some intuition for why you end up always wanting a very big model when you go to predict returns and then use it in a trading strategy. To do this, I'm going to start with some basic least squares background. All right, so we have our least squares estimator. A good way to think about the least squares estimator for kind of understanding the intuition here is to think about it in its system of equations form. Each observation is an equation, right? The parameters are the unknowns. When we're in the traditional environment, P less than T, there's a unique solution. And that unique solution imperfectly fits the data, right? Now, as I increase P to the point where I have the same number of parameters as I do observations, this is kind of the deficiency of OLS that we often think about. I make the parameters close to the number of observations. What happens? Well, now P equals T. I can exactly solve that system. I have a perfect fit of the training data. All right. What I want to be thinking of in this paper is what happens when I make P greater than T. When I make P greater than T, something interesting happens. I get a multiplicity of solutions, right? I cannot pin down the right predictive coefficient from the data that I have. So what do we usually do to deal with this? Well, we introduce some kind of penalty. I'm going to be working with ridge penalties in this framework because ridge penalties are that which plays nicely with random matrix theory. You can't do the theory that I'm doing with, say, a lasso penalty. All right. So what does ridge accomplish for us? It's kind of interesting. You think about ridge, this makes this, so this object, if P is greater than T, right, this is a poorly defined object in the sense that it doesn't have an inverse. I can't do OLS. But if I just add a teeny amount of identity matrix to this, all of a sudden I'm back at a unique solution. Which brings us to an idea that is kind of a fascinating idea, and which is known as ridgeless regression. It's actually describing this least squares estimator when I use an infinitesimal amount of shrinkage. What happens when I do that? Well, it doesn't matter how much bigger p is than t. If I use an infinitesimal amount of shrinkage, what I do is I exactly fit the training data, just like when p equal t. But now I do it by choosing a particular solution, right? If p is greater than t, there are multiple betas that exactly fit the training data. Some have huge variance, and some have relatively small variance. Infinitesimal z, the ridgeless solution, picks that estimator that exactly fits the training data, but has minimum variance among all the solutions that exactly fit the training data. All right, I want us to keep that idea in mind as we go to understanding what this ultimately means for model behavior. All right, so I'm going to skip ahead in the interest of time to this slide. All right, so now what I want to think about is how is a trading strategy that's built from a large prediction model going to behave as a function of model complexity. All right, so on the x-axis here, I have c. So when c is 0, that means I have infinitely more data than I have parameters. As I move to the right here, I hit c equals 1. That's when p exactly equals t. I have the same number of parameters as I have observations. And then when I make c large, that's when I have many more parameters in my model than I do observations. What happens to the variance of a trading strategy that's using predictions from these models? Well, at first, we start off with low variance. Why? Because it's a small model. The estimator has low variance. So when I go and make a trading strategy off of that, it's also going to have low variance. Now, as I start to increase the number of parameters in the model, what's going to happen is that the variance of the estimator is going to start to rise, and that's going to push up the variance of my trading strategy. When I get to p equals t, the variance of that trading strategy is going to blow up, because at p equals t, the variance of the OLS estimator blows up. All right, so you can think about OLS as being a blue line here that's kind of obscured, but it's the one where the volatility is spiking. All right, so that's how we think traditionally about OLS. If I make the number of parameters large relative to the amount of data I have, its behavior explodes, and we try to avoid situations like that. Why? Because the variance of the estimator blows up. But what's interesting, and what's kind of new from the perspective of machine learning, is what happens as we push the parameters way above the number of observations. This is fascinating, and it's not something I ever really understood before working on this paper. The variance of the trading strategy is going to start to come back down. If we can understand why that is, we're going to understand why big models are so powerful. The reason why this happens is as I push C bigger and bigger, what starts to happen? I make the space of solutions that exactly fit the training data bigger and bigger. When I pick the ridgeless solution, I'm always picking the solution that exactly fits the data but has the lowest variance. So as complexity gets higher, I can always find a lower and lower variance solution to pick from because there are more and more solutions to pick from. Which means model complexity actually implicitly regularizes, controls the variance of my predictor. And that controls the variance of my trading strategy. All right. If we understand the variance of what's going on in high complexity models, we understand the hard part. All right. The easier part is to think about what goes on in the expected return of these high complexity models. If I start with a simple model, the expected return from trading on that simple model is going to be close to 0. Why? Because it's a poor approximator. It doesn't have a lot of information on it. If you trade on it, you're not going to get a lot of return. As I enrich the model, I'm putting essentially more effective usage of the information into my trading strategy, and that pushes up the expected return. That essentially caps out at C equals 1, all right? Unless I'm doing some additional regularization, some non-trivial regularization. But the point is, as I make my model more and more complex, I'm using a more and more effective approximating model for the true thing that I don't know. I'm more effectively using information. Why is this not disrupted by the fact that I have many, many parameters? Because the expected return is, well, it's about the bias in the model. It's not about the variance in the model. We know OLS is unbiased. So it doesn't matter how many parameters you put in. You put in more parameters, in expectation, you're going to be getting a closer and closer look at the truth. All right? The cost of those parameters show up in the variance, not in the expected return. And that's something that I think in finance we haven't fully appreciated for a long time. When we think about the cost of big models, it's coming through the variance. There's only benefit for big models when we think about it from the perspective of expected returns. All right, so if we can understand this logic, then the next slide that I'm going to show you is totally obvious, because all I want to do is take the ratio of these two figures, right? And if I do that, I get the Sharpe ratio. We see that when complexity goes up, variance comes down, but expected return is rising or flat. Of course, that means that the Sharpe ratio of a trading strategy that uses lots and lots of parameters is going to be a good Sharpe ratio. All right, so in terms of what I want to convey, the main results from this paper, complexity is a virtue. It starts off when you think about the problem, you cast it in this thought experiment that I originally used. It seems not at all obvious whether or not there would be benefits to using rich models that outweigh the costs of using those rich models, but it's unambiguous. This is true under very weak conditions, right? We have a bunch of general, rigorous theoretical statements in the paper. I showed you this by trying to draw the theory with a reasonable calibration, all right? But I want you to think of these results as being fully general. The last thing I want to do in the time left is to take this to an empirical exercise, all right? So the empirical analysis, I want to show that this works in the most vanilla environment that we could think of. So I'm going to take probably the most standard empirical asset pricing framework that you can think of, forecasting monthly returns on the excess market, okay, excess market returns. All right, I want to analyze the exact empirical analogs to what we did in the theory, so there's going to be some work that we need to do there. But I want to make the conclusions easy to digest. So the conventional setting here is going to be key. What's the conventional setting going to be? Well, we'll work on the market return. Fortunately, in this setting, we have lots of conventional predictors we could bring to the problem. In particular, I'm going to use the Goyal-Welch data. So I have 15 predictor variables here that I'll use at the monthly frequency to form my forecasts. Okay. All right, now there's a little bit of a trick to how I relate the theory to the data, right? Because in the theory, I was able to vary model complexity. But I needed to keep the information set, like that original set of G predictors. I kept that fixed and just changed model complexity. I need to do that in the data as well. So how can I do that? Well, I'm going to use a method from the ML literature known as random Fourier features. It's really just a neural network model. Okay? Here's the way it works. I'm going to take these original 15 Goyal-Welch predictors, which I'll call G. I'm going to produce a bunch of these nonlinear functions of those 15 predictors. How do I produce these functions? Well, I'm going to do it in a way that actually totally evenly distributes the information across many, many generated features. How can I evenly distribute information? Well, I'm going to take a random 15-dimensional vector. I'm going to draw that vector, and I'm going to use that to combine a weighted sum of the 15 predictors. And then I'm going to feed that through a nonlinear function. If I do that one time, I've produced one nonlinear transformation of the 15 Goyal-Welch predictors. If I do it a second time, take a second draw, I can produce another nonlinear transformation, a different representation of the Goyal-Welch data, all right? But because they're both combined in random, they're both constructed in sort of a random way, ex ante, they contain the same amount of expected predictive information. All right. That's going to allow me to look in the data across P, because I can do this once, I can do it twice, I can do it 10,000 times. All right. Okay, so by the time I'm done here, I will have exactly constructed the type of neural network that we often work with in finance and outside of finance. I take my original 15 predictors, expand it out into a bunch of other generated regressors, these S's, these random features. And then once I do that, I'm going to run my ridge regression to forecast the market return. All right, so let's take a look at the results here. One point I should make, I guess, about the empirical setup. I'm going to pick All right, these are, again, this is an out-of-sample exercise, right? So I need to pick a training window. What is that T that I'm going to use? We look at a lot of choices in the paper. In this presentation, I'm going to look at kind of a crazy choice for my training set. T equals 12 observations. Why do I pick T equals 12? Well, there are two reasons. One is that I have to do some really big regressions. If I keep T small, I can get to a higher complexity, right, with a relatively small system. So it sort of saves me some computation. The other reason is I want to show you that the virtue of complexity is there, even in relatively small training sets. Right. So in everything that I'm going to show you, these are going to be out-of-sample results based on rolling 12-month training windows. Okay, so over here, I have a model with one parameter. Over here, I have a model with 12,000 parameters. Just T observations, 12 observations, right? The important thing to recognize is that these data plots look very similar to the theory plots that I showed you before. Let's start with the variance plots. What do we see in terms of variance? At C equals 1, we get a variance spike. All right? Once we move beyond C equals 1, that variance rebounds. Key thing that we need to develop successful out-of-sample machine learning models for finance. 2, expected returns are increasing in model complexity. As I push the complexity higher and higher, expected return is weakly increasing. I put those two together, and I get my Sharpe ratio plot. I can go up to a model with as many as 12,000 parameters and just 12 observations and look at Sharpe ratios that are on the order of 0.4 per annum. You might say 0.4 per annum, that's not that great. That's like the market itself. This is essentially orthogonal to the market. This is all alpha, okay? It's interesting to ask, what does this machine learning model settle on when I use these very high parameterizations? So I'm actually drawing, let's focus on the blue line here, right? What I'm drawing here are the expected returns that are coming out of the model period by period. So these 1 month ahead forecasts as I do my rolling 12-month estimation. Okay, so the blue line is actually the scale that I use in my market timing strategy. When blue is high, I'm taking a big market position. When blue is low, I'm taking a low one. What do we see here? Well, first, it's kind of fascinating. This strategy is long only. Not exactly, but approximately, right? What does it do? It takes large positions in good times and then scales those positions down to about 0 in bad times. Right? Now, I thought this was pretty fascinating because there's this beautiful Campbell and Thompson paper that says, listen, Goyal and Welch are complaining that you can't predict returns with the standard predictors. Well, John said that's because sometimes you get these really crazy ERs that get way negative. Just cut those out. Force your predictions to be positive. The model learned to do this without me giving it John's constraint. All right? That's why it's doing so well out of sample. And it's interesting to point out that the way it does this in particular is that it divests ahead of recessions. Okay? So there are 15 recessions in this sample. It basically divests to a weight of 0 in the market leading up to each of them. The only one it doesn't, there's this late 40s one, an 8-month recession. Okay. So we could talk about how this reconciles with the literature. I'm a little bit short on time, so maybe I can engage with that in Q&A or something like that. I want to point out that this is part of a broad agenda. So I'm showing you these empirical results. This is primarily a theory paper. I showed you these empirical results for the market. We have another paper where we show that these patterns that I just drew for you, they show up in every asset that we've looked at. We've looked at futures of all sorts, commodities, currencies, foreign equities, bonds, credit. These patterns show up across the board. So that's the virtue of complexity everywhere. Second, the idea of introducing complexity in asset pricing really begs you to introduce it into an asset pricing model, into an SDF. So we recently, many of you were actually at this NBER presentation where I recently presented that. And then there's some more statistical trimmings that we can add on top of this. I'm going to wrap up with a very short statement of conclusion. So first of all, I want us to emphasize that this boom in ML research for finance is a good thing. We shouldn't be so skeptical of these gains from using ML and asset pricing models. The theory tells us we should actually expect those gains. All right? Now, one thing I would add is that this is not a license to add arbitrary predictors to a model. The way you should build a complex model is to put in all the plausibly relevant predictors, but put them in nonlinearly. Add these big, expansive approximations that allow for nonlinear usage of whatever information that you do think is relevant. All right. And the last thing I want to say comes back to the motivation slide that I had in the beginning. I'm going to talk about two quotes from George Box. Right? So the first one we've probably all heard. All models are wrong, but some are useful. Right? The second one I love because it kind of would be a very nasty criticism of this paper, right? Since all models are wrong, the scientists cannot obtain a correct one by excessive elaboration. In contrast, you should seek an economical description of natural phenomena. The ability to devise a simple model, but evocative model, is the signature of a great scientist. Over-elaboration, over-parameterization is the mark of mediocrity, right? Maybe we should be calling this Occam's blunder, because Box himself tells us all models are wrong. But if all models are wrong, I just showed you that you should use the biggest model possible. All right, so I'm going to wrap up with that thought. Very much looking forward to the discussion.